In our previous lesson, we talked about how the bonding of atoms in covalent bonds comes through the sharing of electrons. We used the example of hydrogen, which due to its single electron can only form a single bond. We're going to expand this understanding to all valence electrons and form the basis of both molecular orbital theory and valence bond theory in today's lesson. While a bond between hydrogens only has s orbitals, most of our elements use some combination of their s and p orbitals, their valence orbitals, for bonding.
We draw fairly simplistic pictures of these orbitals, but in reality, they are representing a probability density for finding an electron. A 1s orbital may have most of its electrons in the sphere shown, but near the center, there is a much higher chance of finding an electron than on the outside. Our simplest orbitals are of the s type. S orbitals are easy to work with because they have the same phase all the way around. This means that no matter which orientation an s orbital is bound, it will have the same overlap and the same bonding characteristics. Super simple, but only hydrogen atoms really use s orbitals like this to bond. So most covalent bonds are directional. When we have higher principal quantum number, n, which is essentially just the period, our s shells are just getting bigger. P orbitals are a little bit more complicated. They have two lobes of opposite phases, with a nodal plane that separates them at the nucleus. A node, or a nodal plane, is just a place where electrons cannot go. There are 3 p orbitals, and the 3 orbitals are orthogonal, which is the three-dimensional version of perpendicular. Together, they roughly make a sphere.
When orbitals interact, they lead to bonding, but they can also lead to antibonding. When orbitals interact in phase, this essentially amounts to adding those two orbitals together. When they interact out of phase, it essentially amounts to subtracting. In-phase interactions result in increased electron density between the atoms, which draws them together, a bond. Out-of-phase interactions result in a nodal plane, a place where there's no electrons between the atoms, and that's the opposite of a bond, which we call an antibond. These form the basis of understanding a lot of the reaction geometry in organic chemistry. We call the underlying theory about adding or subtracting orbitals to describe molecular orbitals molecular orbital theory.
Molecular orbital theory is a way that we make sense of the energetics that we see resulting from bonding, but is an extension of the same math that gives us atomic orbitals in the first place. The first assertion of molecular orbital, or MO theory, is that atomic orbitals of similar energy may interact. This is not really a game-changing assertion, since valence orbitals tend to have similar energy anyway. MO theory next states that atomic orbitals form linear combinations, which are just the additions and subtractions that we talked about in the last slide. Every time we combine atomic orbitals, the number of atomic orbitals in is equal to the number of molecular orbitals out. In the example shown, we combine 2 hydrogen s orbitals and we end up with 2 molecular orbitals, one bonding and the other antibonding. Atomic orbitals can overlap with different symmetry. If their overlap has a circle cross-section in the bond axis, like what's shown above, it is a sigma bond. If 2 p orbitals overlap, they will have 2 separate areas of overlap above and below the bond axis, a pi bond. Pi bonds can also happen with d orbitals, but we don't really worry too much about them in organic chemistry. When overlap is along the bond axis, a sigma bond, it is much more significant than the overlap created by p orbitals. Because the overlap is low, the stabilization from pi bonding is less significant, and the destabilization from pi antibonding is also less significant. In molecular orbital theory, we would normally need to do complex calculations for every single orbital. That's not bad with H2, but even with a simple organic molecule like ethane, we have 14 valence electrons and 4 core electrons to deal with. Valence bond theory simplifies this with a few basic assumptions that generally hold true. We're always going to assume that hybridization is going to match the number of groups of electrons, which we can get from valence shell electron pair repulsion theory. We are also going to ignore all of the core electrons since they tend not to bond. We think of forming new orbitals by mixing adjacent atoms one at a time. So our picture of ethane can be simplified drastically. In this picture, our single bonds all come from sigma bonding orbitals, and the empty sigma star orbitals are not shown, since there are no electrons in them. Now, having introduced molecular orbital theory and valence bond theory, you might think that they don't add much to the valence shell electron pair repulsion theory that we've already learned. So far, these can explain some things about spectroscopy that VSEPR theory cannot, but the real power in these theories comes from the way they deal with the p orbitals that are unhybridized, which we'll talk about in our next lesson. Let's think about why that is. The more overlap that occurs between orbitals, the stronger the bonds. Trouble is, the s orbitals are fairly buried compared to the p orbitals. To make the s electrons more accessible, atomic orbitals within the same atom hybridize. That is, they add to each other. Look at the overlap between the s and p orbitals shown. The places where blue and red overlap are in phase, and the resulting hybridized orbital has increased electron density on that side. The overlap between white and red are out of phase, and the resulting hybridized orbital is out of phase on that side. The p orbital can mix in both directions with the s orbital, resulting in two sp hybridized orbitals that point in opposite directions, hence 180 degrees. Since one s orbital and one p orbital are used to make two sp orbitals, each sp orbital will be half s and half p, but there will still be two orthogonal p orbitals left untouched.
Figure 1.17 from your text shows what happens when two sp hybridized carbons come together in the acetylene molecule. In the top left, there are two sp orbitals shown in green on each carbon. One from each carbon can overlap head-on-head to form a sigma bond, labeled as an s bond in the top right of the image. There are also two p orbitals, each shown with one lobe red and the opposite phase lobe shown in blue. The two unhybridized p orbitals can also overlap to form two separate pi bonds, labeled as p in the top right. So any triple bond contains one sigma bond and two pi bonds.
Sigma bonds and pi bonds behave very differently, and this makes a big difference for molecular structure. Sigma bonds have the exact same overlap regardless of what their orientation is, but as soon as you rotate one p orbital relative to another, no overlap occurs and the pi bond is broken. Rotation around a double or triple bond, then, amounts to a reaction. A bond must be broken and reformed. There is a significant energy cost to this. It is possible, but it doesn't happen appreciably at room temperature. So for our purposes, you cannot rotate around a double or triple bond. This leads us to molecules that are connected in all the same ways, but are actually separate molecules with different chemical and physical properties. Take these 1,2-dichloroethanes as an example. Each carbon is connected identically to a chlorine, a hydrogen, and double to another carbon. But the two molecules have different relative directions for the chlorines. The first has them on the same side, which we call cis same side. The second has the chlorines on opposite sides, which we call trans. These are our first example of stereoisomers, molecules that are connected the same, but in different orientations. Depending on the bonding needs of an atom, the atom may hybridize these p orbitals as well. If two p orbitals are mixed with the s orbital, the result is an sp2 hybridized orbital. Each will only be a third s and 2/3 p. The electrons are held out a little farther with the increased p character, so the bonds are longer. Notice that there is still one p orbital left as well.
We can see sp2 hybridization in action in the molecule ethylene shown below. Again, we see the hybridized orbitals, in this case sp2, labeled in green. There are three different sp2 hybridized orbitals on each carbon center, but we have one p orbital that's remaining behind. It wasn't part of that hybridization. So the sp orbitals can interact head-on-head to form a sigma bond, again labeled as an s bond, and the p orbitals can interact side by side to form a pi bond.
When every valence orbital gets mixed, we end up with four sp3 orbitals. Notice that since we have p orbitals contributing in all of the 3 dimensions, our orbitals are arranged in 3 dimensions. Each orbital is only 25% s and 75% p, so they are all held further out than the other hybridized orbitals. There are no p orbitals that are remaining.
In the example of ethane, we can see this sp3 hybridization at work. In this case, every one of the p orbitals is part of the sp3 hybridization. That's the p3 part. And so every one of our orbitals is 1/4 s and 3/4 p, and they all are identical to each other. So when we interact these two carbon centers, they can interact only through sigma bonds, which is why we only have a single bond.
Notice the shape of hybridized orbitals compared directly to the geometries predicted by VSEPR theory. It's nice when the math lines up with reality. So sp hybridized orbitals are 180 degrees, sp2 are 120, and sp3 orbitals are 109.5 or tetra. With this in mind, we can look at any atom's geometry and use it to indicate the hybridization of that atom. Pause and try to do this yourself, and then continue. For example, we see that A has 4 bonds to carbon, the 3 carbons shown, and then also hydrogen that's not shown. That would make it tetrahedral. Tetrahedral geometries indicate sp3 hybridization. B is linear, indicating sp hybridization, with the remaining 2 p orbitals forming the additional bonds to nitrogen. C is trigonal planar, indicating sp2 hybridization. D is also sp2, since we care about the electron geometry for hybridization rather than the geometry of the atoms alone. Finally, E is sp3. The molecular geometry of an atom can also play a role in its reactivity. The molecule shown is cyclopropane. Cyclopropane consists only of carbons with 4 groups attached. Every one of them has 2 bonds to carbon and 2 to hydrogen. Normally, this would mean that every bond is 109.5 degrees, the maximum distance 4 groups can separate in 3 dimensions. But what are the interior angles of an equilateral triangle? Always 60 degrees. This difference in geometry costs the molecule a great deal of stability, and the molecule is much more reactive than it would be if it was not in a ring. It is important to note that while many hybridized orbitals of an atom will become molecular orbitals, not every atomic orbital has the correct energetics or orientation to form a new molecular orbital. Lone pairs tend to not have formed any molecular orbitals, which makes sense since they don't participate in any bonds. We call them non-bonding orbitals. While they may have been stabilized by some hybridization, like this example where the non-bonding orbitals are sp2 hybridized, they will not increase or decrease in energy from there. For this reason, lone pairs are often even higher in energy than pi-bonding electrons, and can often also participate in reactions as the HOMO. The more s character an atom has, the closer the electrons are held. These are functionally more electronegative, so an s orbital can stabilize more negative charge than a p orbital, and everything else in between follows the same trend. sp orbitals are more electronegative, but that also means that an H attached to an sp orbital is easier to remove, since we can more easily stabilize the anion that's left behind. We can alter the acidity of a CH bond from alkanes, which are not at all acidic, to alkenes, which are still not appreciably acidic, to alkynes, which are just barely acidic enough to form a carbanion in really strong bases. That's pretty amazing because we'll very rarely see carbanions, and they allow us to form carbon-carbon bonds. As we discussed in this chapter, molecular orbital theory gives us much of the same information obtained from VSEPR theory, but it also allows us to determine information about reactivity that we can never access from VSEPR theory.